Hello, this is Jan-Magnus, and today I want to answer the question: how many lines in space meet four given lines? I have here four skew lines, and I get rid of one of them. Three skew lines in space define a unique hyperboloid of one sheet. And if we put back in the fourth line, we are so lucky because I arranged it that way. The fourth line intersects the hyperboloid. We can also have situations where it touches the hyperboloid and has only one intersection point, and the line may not intersect at all the hyperboloid. Okay, but we have two intersection points, A and B. And the tangent plane to the hyperboloid at A picks out two lines on the hyperboloid. One of them is of the other family of lines from the three we started with, and this will intersect all lines of the other family, in particular the three we started with, and the fourth was already on there. So this meets all four lines. And the story is the same for the other intersection point, and we get the line of intersection between the hyperboloid and the tangent plane at B, picking out a line of the other family of lines to the family of lines that include the three we started with. Now we include all the intersection points and take away the hyperboloid, and we can check that it all fits. We have two lines meeting four given lines in space. If you want the answer to be prettier, you can work with complex projective three space, and P1 cross P1 is then the hyperboloid of one sheet, and then you get that all lines meet the P1 cross P1, and you always get two lines meeting four given lines up to multiplicity. That is, you still have the tangent problem. This question is one of the first questions in non-trivial questions in enumerative geometry. A subfield of intersection theory. So, if you want to hear more about the technical details of the GeoGebra app I used to animate this, we have the lines given by 2 points. A1 and B1 gives the first line, A2 and B2 give the second line, A3 and B3 give the third line, A4 and B4 give the fourth line. And then I take the difference, B1 minus A1, call it C1, and A1 vector product B1, call it D1. The 6 numbers from the coordinates of C1 and D1 are what we call the Plicker coordinates of the line. And similarly for the second, third, and fourth points. We only need the Plicker coordinates of the 3 first because we have the equation of the hyperboloid in terms of the Plicker coordinates. The Plicker coordinates are really coordinates of the embedding of the Grassmannian of two spaces in 4 space, or equivalently lines in projective 3 space. And this number A here is always 0 because it's called the Plicker relation. So that means that these 6 numbers, since it's in a P5, really gives a 4-dimensional variety of lines in space. The relation cuts the dimension from 5 to 4. It's a quadric in P5. Otherwise, the argument is the same. Real or complex 3 space with lines. I have an answer to a math stack exchange post that will be posted in the description. And I entered this as my entry in Grant Sanderson's Summer of Math exposition. Bye.